Exam 3 is next Friday. Next Monday. Next Monday, 12/9.
Just leave it open whenever we feel like it.
Yeah. And the topics are everything up through internal loads. Any questions about the test? Okay, so today I'm gonna go through that internal loads problem. You can sort of check what your thinking was on this. If you don't have your solution with you, you should compare the way I go about this to your solution. But this is about as complicated as these internal loads problems get. Remember, this is the one we did the structure, and then we calculated the internal loads on all the members, and this was the last one we hadn't done yet. And then if we have a good chunk of time left after I'm done with this, then we'll get into friction. Okay, so from last time, we have this beam with a force over here of negative 200.40, negative 34.28. And then just an upward force at the middle of 266.67. A force at the end that I don't have written down. It's not going to come into the internal loads. A triangular distributed load with a magnet with a maximum of 600 newtons per meter. And a distributed load for the weight of 49.05 newtons per meter. Okay, so that's the free body diagram of the whole thing before we turn any of these distributed loads into point forces. How many cuts are we going to make? 2. Yep. So there's the endpoints and the one place where, in this case, we have both a point force and a change in distributed load function. So the only cuts are representing there and there. I don't have written down how long this thing is. 2 meters?
Yeah.
I think that's right.
Yeah. Mm-hmm.
So the first cut is for x's between 0 and 1. And this one's easy. There's not much going on here. Negative 200.40, negative 34.28. And then you have this distributed load with a height of 49.05. The whole thing has a length of x. And then the internal loads. And we need to turn that distributed load into a point force. It has a height of 49.05, a width of x, The centroid is right in the middle. So from the end, this distance is x over 2. And the area is the area of a rectangle, the height times the width. So 49.05 x. And so now we can rewrite this replacing that distributed load with the point force. So over here we have negative 200.40, negative 34.28, a downward point force at the middle of 49.05 x, and then the internal loads. So Newton's second law says negative 200.40, negative 34.28 plus 0, negative 49.05 x plus t negative v is equal to zeros. So the internal tension is 200.40, and the internal shear force is negative 49.05 x minus 34.28. And then the moment equation, we have a clockwise moment, so negative with a moment arm of x over 2 times the downward force of 49.05 x plus m minus vx is equal to 0. And so m is equal to 24.525 x squared plus v times x, so that is minus 49.05 x squared minus 34.28 x. And if you simplify, m is equal to negative 24.525 x squared minus 34.28 x. Dm dx is equal to v, so that's a good sign. Negative dv dx is equal to q, which in this case is just that constant. So that's a good sign. Okay, any questions about the first cut? That's way easier than the second cut. So cut 2 is for x's between 1 and 2. At the left end, we have negative 200.40, negative 34.28. Now we have new stuff happening at the midpoint. And remember, the midpoint of this overall beam is not the midpoint of this cut. Okay, the midpoint of the overall beam is 1 meter from the left end. So 1 meter from the left end is, let's say, here. We have an upward force of 266.67. Then we have part of this triangular distributed load, but not all of it. And we'll think in a second about what the maximum height is of that triangular distributed load. And then we have the distributed load representing the point force, the weight force. And this has a magnitude of 49.05. And then we have the internal loads. Okay, so now we have to come up with, for the height of that triangular distributed load, we have to come up with a function for the line that defines that hypotenuse. Well, the slope is, we can see it goes from a height of 0 to a height of 600 over 1 meter. So the slope is going to be 600. What about the y-intercept? Well, remember that this line, this place here at the left end is our x equals 0. Okay, so the question is where this line would hit that red x equals 0 line. Okay, and it wouldn't be at 0 in this case. It would be at, I guess, negative 600. Okay, it might take a little more figuring than that in the case where this didn't start at the midpoint. But at the midpoint, it's pretty easy because of the just symmetry of it all. And so this height over here is represented by the function 600x minus 600. And this whole thing has a length of x. We already figured out what's going on for this rectangular distributed load, and everything that we did in that first cut is still the same here. The point force representing this one is going to be at the midpoint of the cut, and the magnitude of the point force is going to be 49.05x. So I'm not going to draw that again. But the triangle, we should think about this. The biggest new wrinkle here is that the width of this triangle now is no longer x. Okay, the width of this triangle is, it only starts at x equals 1. Okay, and so the width is x minus 1. It's that full distance minus all the stuff before you get to 1. And the height we have is 600x minus 600. So first, the centroid. We know that it's 2/3 of the way from the left end. So we can write this distance here as 2/3 times x minus 1. But remember, if you treat that as the moment arm, you're going to get the wrong answer, because our moment arm for calculating the moment has an about point all the way over here at x equals 0. So it's this plus the distance from the left end to the midpoint. So it's this plus 1. Okay. And then the area of this thing, well, the area of a triangle is the base times the height divided by 2. I'm going to think of this as 600 times x minus 1. So the area is x minus 1 times 600 times x minus 1 all over 2. And now we can simplify that a little bit. This is equal to 300 times x squared minus 2x plus 1. (300x squared minus 600x plus 300). Okay, so we've done all this work and we're almost ready to draw our final free body diagram, you know. So here's the cut. Over here we have negative 200.40, negative 34.28, an upward point force of 266.67. Then from the midpoint of the cut, not the full beam, we have a weight force down of 49.05x. And then finally, we have that point force representing the triangular distributed load that has a magnitude of 300x squared minus 600x plus 300. And then the internal loads. Any questions about that? Okay, well, let's figure out these moment arms. So this one, this is the point force representing the weight distributed load. What's that moment arm? Yep, that's just at the midpoint of the cut, so that's x over 2. What about this one?
Just
1, yep, perfect. And now what about this one? Well, we know that from the 266.67 to this force is a distance of 2/3 times x minus 1. We want to add 1 to that. And so this comes out to be, I'm going to write it as, you know, so if you multiply this out, it's 2/3 x minus 2/3. We're adding 1 to it. So it's 2/3 x plus 1/3. So that's how I'll write this. 2x over 3 plus 1/3. Okay, so Newton's second law says negative 200.40, negative 34.28, plus 0, 266.67, plus 0, negative 49.05.
X.
Thank you. Plus 0. And now, okay, this gives us a magnitude. The unit vector is in the negative y direction. So it's this magnitude times the unit vector 0, negative 1, which switches the signs of all of these terms. So this is 0, negative 300x squared plus 600x minus 300 and then plus t minus v is equal to zeros. 1, 2, 3, 4. Yes. Okay, so from the x equation, t is equal to 200.40. From the y equation, the shear force is equal to negative 300x squared minus, nope, plus 600x minus 300.
So minus 49x from the weight.
Yep. Minus 49.05x plus 266.67 minus 34.28. Okay, so now we got to group some stuff. There's only one x squared. There's two x's. There are three constants. So the shear force is negative 300x squared plus 550.95x minus 67.61. Negative dv dx is equal to, so 600x plus 550.95. The total distributed load is that. So that works. And then the moment, this is the one we've all been waiting for. There's a clockwise moment from that 49.05x. So that's negative moment arm of x over 2 times 49.05x. There's a counterclockwise moment from the 266, and that just has a moment arm of 1. And then there's a clockwise moment, so negative, with a moment arm of, I guess I could write this for calculations. I'll write this as 1/3 times the quantity 2x plus 1. And then we're multiplying that by this force, and I guess I'll write that as 300 times the quantity x squared minus 2x plus 1. And then plus m minus vx is equal to 0. So negative 24.525x squared plus 266.67 minus the 1/3 and the 300 gives us just 100. And now we got to FOIL this thing out, distribute these. So 2x times x squared is 2x cubed. 2x times 2x is, times negative 2x is minus 4x squared. 2x times 1 is 2x. Now 1 times all these things, so 1 times x squared is x squared. 1 times negative 2x is negative 2x. 1 times 1 is 1. Plus m minus vx is equal to 0. I'm just going to write all this stuff again and just simplify that middle thing. So 2x cubed minus 3x squared. The x's cancel. Plus 1. And then plus m minus vx is equal to 0. So m is equal to 100, I guess, times 2x cubed. So I'll make this 200 x cubed minus 300 x squared plus 100 plus 24.525 x squared minus 266.67, and then plus Vx, which is minus 300 x cubed plus 550.95 x squared minus 67.61 x. X cubes, we have 1 there, 1 there. Squares, we have 1 there, there, and there. Linear terms, just that one. And then we have the constants. So m is equal to minus 100 x cubed plus 250.95 x squared minus 67.61x minus 166.67. Okay, so dmdx. The first term.
Instead
Yep.
of 250.95x squared, it's supposed to be 275.475. I think you forgot to include the 24
Okay, where's that one?
in the middle, highlighted in the green box.
Okay. The 24.5.
550 minus 300 would be 250.
Oh, in the
Add 24 back in.
550.
Far right,
Oh, he's right.
second from the bottom.
You have three
Yeah.
squared terms and you only added the outer.
Oh, okay, yes. Okay. So 250 and just add on the 24.
Yeah.
Okay, 250.95 plus 24.525. So 275 point, let's call it 48. Yes, thank you. Okay, so just go term by term. dm dx for that first term is negative 300x squared. Yay. For the second one is, that's going to be 550 point, yeah, that's pretty close. 550.9596x minus 67.61. So the derivatives work. Whew. Okay, that's a mess. Okay, so what about in this case where it's going to get this ugly? What about the thought of, so what we would give up is we would give up the ability to check our work using the derivatives. But what if we just use these derivative relationships right from the start, you know? We're lazy people, so we'd kind of prefer not to do this if possible, you know? So let's see how that looks. Well, we have this, let's say that we go to, so could we do this by integration instead? Let's say that we calculate V. That one isn't too bad going through Newton's second law. So let's say we go to that middle step. We do the derivative check. We're confident with that shear force. And then we say M as a function of X is equal to the integral of the shear force with respect to X. Okay, so M is equal to the integral of negative 300x squared plus 550.95x minus 67.61 dx. Okay. So taking the, antiderivative is not going to be the hard part. The hard part is going to be in these always just matching up the boundary conditions. So M is equal to negative 100 x cubed plus 275.4 0.475 x squared minus 67.61 x plus our constant of integration. And that's the thing that we have to figure out. Well, what do we know about the, so this is only valid on the interval between x equals 1 and x equals 2. So we would like to use that boundary condition at x equals 0, but it doesn't mean anything here. Okay? So instead, we have to use what that shear force is at x equals 1. Okay? So at x equals 1, and we're going to use the function for this cut. Where is it, our shear force? We have, so plug in x equals 1 for that shear force formula, negative 300 times 1 plus 550.95 times 1 minus 67.61. And we get a value of 183.34. That does not help. Oh, I know what we want to do. No, forget all that. Sorry about that. That was a detour. So what we need really are the boundary conditions. We need boundary conditions on the moments. The boundary condition on the shear force isn't going to help us. So what can we say about the bending moment at, we don't know what the bending moment is at x equals 1. But we do know what the bending moment is at x equals 2. 0, because there's no point couple at that point. So pretend I didn't say any of this. We want to look at x equals 2. There's no point couple. So the bending moment at 2 has to be equal to 0. So, okay, now we're going to go negative 100 times 2 cubed plus 275.475 times 2 squared minus 67.61 times 2 plus c is equal to 0. And, bless you, we get that c is equal to negative 166.68. Oh my God, it worked. And so m, as a function of x, is negative 100 x cubed plus 275.475 x squared minus 67.61 x minus 166.68 with a round off error of 0.01 between these two. Okay. Well, anyways, that was a lot better than the first way. Yes.
Why do we know this is zero? That we're setting any?
Because remember those 5 checks that I gave you, the ones we use all the time are the derivative checks. But then the other 3 are the shear at endpoints. The internal tension is equal to 0 if and only if there are no horizontal point forces at the endpoints. Does this ring a bell? Remember this? The shear force is 0 at endpoints if there's no vertical point force at that endpoint. And the bending moment is equal to 0 if there's no point couple at that endpoint. And so just looking at this beam, we have forces at the 2 endpoints, but no bending moment, so we know it has to be 0. Any other questions about that? The test next Monday is going to be 5 problems like this. No, just kidding.
But how are we supposed to check our work?
Yeah. Yeah, well, exactly. You can't check your work then. I mean, so you're giving up a lot. But, I mean, I would use the old way. You know, I just always use the old way because it's better to be sure than to be fast always, I think, as an engineer. I really can't imagine any case where people are like, it's okay to get 1/5 of your problems wrong, just be fast. I just can't imagine that scenario, you know? So I always think it's better to do the Newton's laws approach, and then you have the derivative check there. So, but this is just how it would work.
But you'll still like give us credit if we use this to get an answer, right?
Yeah.
Okay.
The right answer.
If you're right.
Yeah. Even if you get a wrong answer, to be honest, I mean, if you do all the things right and you just do like if you get to this point and don't add these 2 things, and then like my answer would have been wrong and I would have been really unhappy about it, but I wouldn't take off points on a test for a mistake like that, you know? So, yeah. I'm always secretly proud of people when you don't take my advice. So, yeah, if you go that way, I'm like, all right, that's the spirit. All right. Any other questions? Okay, let's stop there, and we'll just start on Wednesday with friction. If you have any problems, homework problems or whatever that you want me to talk about, bring them to class, and I'll do those too.
Do you want to run through that weekly assignment problem real quick?
Sure.
I'm kidding.
Oh, yeah.
Do the whole thing, you know?
Yeah.
Right. Oh.
I'll say I was at the.
I have to